Hello! In a previous video, I explained how the floppy bridge code inside of UnitU worked. During that video, I mentioned DMA. No, not that DMA. In this video, not that DMA either. In this video, we're going to explore what DMA is, where it's used, and why it's so important. First things first, DMA stands for Direct Memory Access. But before we look into what it is, let's look at how things worked before it existed or without using it. We'll start by looking at a very simplified diagram of computers, sometimes referred to as von Neumann architecture. That diagram pretty much sums up almost every computer, games console, laptop, tablet and phone I've ever seen. But if we dig a little deeper, we might end up with something a little more complex. No, not that complex. This is a somewhat more simplified view. But essentially, you've got several devices connected together on what are called the address and data bus. These buses are physical wires or connections between devices. The size of the address bus, i.e. the number of wires, controls how many addresses are available. For example, the total amount of RAM. The size of the data bus determines how much data can be read or written to at a time. In this example, we're going to assume that this system uses memory-mapped I/O. That means that devices like sound, graphics and disk also appear as if they were part of the RAM. This is a very common method for communicating with hardware. Another method is I/O mapped I/O, but we're going to ignore that for the sake of this video. Now, because they're all connected together, the first thing you'll notice is that only two devices can communicate with each other at the same time. For example, the CPU can communicate with the RAM, or the CPU talking to the disk. If I'm the CPU and I want to read, for example, 20 bytes from RAM, then there's a sequence I must perform, like this. Firstly, we have to place the address of the start of the RAM on the address bus. Then we can read back from the RAM by reading back from the data bus. That's 1 byte. Now, to read the next one, we need to increase the start address, write that to the address bus, and then read from the RAM again. So to read the entire 20 bytes, we'd have to repeat this process 19 more times, and there's a fair few instructions required to make this happen, which means it's not very efficient, slow, and time consuming. And while this is going on, for this to be as fast as possible, the CPU can't be doing anything else. Now, the above loop may have been okay in the earlier ages of computing, but generally we don't want to read just the RAM. Let's say you wanted to draw an image on the graphics card that is currently in RAM, or you want to play some digitised audio that is also in RAM. Well, we'd have to set the address bus to where the start of the audio was located. Then we need to read a byte from the data bus. Then we need to set the address bus to the address of the sound device, although in some systems this was accessed a different way. Then we need to write this data onto the data bus. And then we need to repeat this process for the entire piece of audio. And not only that, at the correct speed, or the sound wouldn't play correctly. Some devices did have internal RAM that you could write the sound to, but for the purpose of this example we'll ignore that. Clearly this approach isn't going to scale well beyond very basic systems, although it was used. So, DMA was invented. Now, the idea being, what if you could tell another device, for example a DMA controller, the source and destination addresses and how much data it has to transfer, and then have it perform the transfer instead of the CPU, and at a much faster rate, leaving the CPU free to do something else. Then, when the transfer is complete, have this DMA controller notify the CPU so that transfer doesn't actually need to be monitored. Well, this is exactly what DMA is, and it splits into two types. The first, and most basic, is called third-party DMA, and it is literally as we've described. The CPU would communicate with the device, or sometimes a special DMA controller chip, and tell it to copy one or more words from or to another address. The device performing the DMA would then go about doing this, and when finished would usually generate an interrupt request, which the CPU could use to do something as a result of the transfer completing. The alternative to this is first-party DMA, also known as bus mastering. This time, the CPU or one of the attached devices can be granted control and ownership of the memory and data bus. While the device has this ownership, no other device is allowed to take control. This exclusive access allows the device to write directly from and to system RAM without the CPU being involved. The big difference here though is the device can initiate the transfer all on its own, without the CPU. But not all things are as easy as they seem. The only restriction here is that some special measures need to be put in place to make sure other devices, including the CPU, don't try and communicate with the bus while this is going on. For example, some systems would simply halt the CPU while this transfer was in progress. This data transfer can occur in several different ways, again, each with their own advantage. We'll start with burst mode. An entire block of data is transferred all in one go, but while this is going on, for safety, the CPU is usually inactive. But that wastes a lot of CPU cycles which could be used for something else. So instead, there's several other methods. One example is cycle stealing mode. This is a little bit more sneaky, but it's not as fast as burst mode. When the device wants to transfer data from and to the CPU, it asks for control of the bus. And when granted by the CPU, it will copy usually one piece of data, the width of the data bus, and then release control back to the CPU. Then it would repeat this process until the transfer is completed. This is great, as the CPU can then carry on working mostly, but still not at full speed. There's also a mode that's completely transparent to the CPU. In this mode, the device only transfers data when the CPU is doing something else that doesn't use the address or data bus. The CPU never stops working in this mode, but the transfer may take a little bit longer as the speed of the transfer may be a little bit less predictable. Systems like the Amiga have a different transparent trick. It uses an interleaved approach. The entire system is run by a system clock which sends out pulses at a fast but steady rate. Access to the data and address buses, at least in theory, is split in two. On the even clock cycles, the CPU is allowed to access the address and data bus exclusively, and for the odd cycles, the various custom chips have control. Agnus, the DMA controller, is in charge of this time slicing, but in reality, depending on things like screen modes, some cycles are actually stolen back from the CPU for other transfers. That, however, is a topic for another day. When I was in college learning to program in Turbo Pascal in MS-DOS, still massively into Amiga tracker music, I wanted to create my own mod file play routines. The computers I was using back then only had a PC speaker, and to play the audio via this was very CPU intensive as you had to write the PCM audio data to the PC speaker in real time. Later on though, I got access to PCs with a Sound Blaster 16 inside. I managed to get access to the PC GPE, better known as the PC Game Programmer's Encyclopedia. This vast collection of text files and example code contained details on programming various aspects of the PC. One of the documents explained how to communicate with the Sound Blaster to play audio, and even how to use the DMA to make this transfer very efficient. The Sound Blaster included a DMA mode called Auto-Initialized DMA, which, once set up, would keep re-requesting the same block of memory over and over in a loop, until told to stop. The way it worked was, you would allocate some memory, and then split this block of memory in half right down the middle, and you'd program the DMA controller to transfer the entire block of memory, but you'd program the Sound Blaster to only be aware of half of it. The Sound Blaster would then generate an interrupt each time half of the data had been played. Using this interrupt, I was able to call my mixer routine to create the next block of audio and overwrite the block of memory that had just been played, whilst in the background the sound card transferred and played the other half of the block. I didn't invent anything here, this was the way to achieve clickless audio, and it worked great. The CPU almost had nothing to do while this was going on, leaving lots of CPU time for a pointless display of the tracker module being played. So there's a lot more I could tell you about DMA, and several further improvements exist to DMA to take advantage of the advances in hardware and CPU architecture. But I hope that's been a good background into the subject. Why not consider setting up your own DMA transfer to support me? I call it Patreon. Anyway, thanks for watching, and I'll see you in the next one.